In this problem, we have a conducting spherical shell. The inner radius of the shell is A, the outer radius is B. At the center of the shell, there is a point charge, positive charge with charge Q, capital Q, and the total charge on the conducting shell is equal to negative 3 times Q. In part A of the problem, we're going to calculate the magnitude of the electric field in 3 different regions. First, in the region for R less than A. Second, in the region for R in between A and B. And third, in the region where R is greater than B. So that's outside of the conducting shell. Let's apply Gauss's law for the region R less than A. That will be an imaginary spherical Gaussian surface around the point charge Q within the gap, basically. So again, Gauss's law says that the flux through this Gaussian surface is going to be equal to the charge enclosed divided by epsilon 0. So let's set up our equation. Here's Gauss's law, flux equals Q enclosed divided by epsilon 0. Now the radius of the Gaussian surface is the variable R. So let's rewrite the equation in terms of the given variables. The formula for the spherical surface is 4 pi r squared. We multiply that by the magnitude of the electric field. That's the flux. And that's going to be equal to capital Q, which is the enclosed charge, divided by epsilon 0. Let's rearrange and isolate capital E. Electric field magnitude capital E is equal to Q divided by 4 pi epsilon 0 r squared as expected. This is the electric field magnitude due to a point charge at a distance r. And the direction of the electric field will be outward because the enclosed charge is positive. Next, let's determine the electric field in the region R in between A and B. While that is the region within the conducting material, and electric field in a conducting material is equal to 0. So in this region, the electric field is going to be equal to 0. Finally, for the region R greater than B, we draw another Gaussian surface, this time a spherical surface outside of the conducting shell. And again, we apply Gauss's law, flux equals Q enclosed divided by epsilon 0. Let's rewrite our equation in terms of the given variables. Again, the radius of the Gaussian surface is R, so that's the variable R. And the enclosed charge is the total charge, that's plus Q minus negative 3 times Q. Now note that I have absolute value signs around Q enclosed. Why? Because in this problem, capital E is defined as the magnitude of the electric field, so I'm keeping everything positive. So the absolute value of the enclosed charge is going to be equal to 2 times capital Q without the negative sign. Now let's rearrange our equation and isolate E. And here's the result. Electric field magnitude in the region R greater than B as a function of R is equal to 2 times capital Q divided by 4 pi epsilon 0 R squared. The direction of the electric field vector will be inward towards the shell. Why? Because the enclosed charge is negative. It's equal to negative 2 times Q. In parts B and C of the problem, we're going to calculate the surface charge density of the inner surface of the spherical shell and the outer surface of the spherical shell. Now, if you think about it, this is a conducting shell, and everywhere within the conducting material, the electric field has to be equal to 0. So the electric flux through this Gaussian surface within the spherical shell inside the material has to be equal to 0, meaning charge enclosed within this Gaussian surface has to be equal to 0. But we have a point charge of plus Q at the center. So then how can we have total charge enclosed to be equal to 0? Well, negative charge Q, so equal and opposite charge from the rest of the conducting sphere, is going to be placed in the inner surface of the sphere such that the charge enclosed within the Gaussian surface that you can see in the picture, the black dashed surface, circular line, is equal to 0. So again, by how much of this charge is going to be deposited in the inner surface, that will, the amount of charge that will cancel out the charge at the center, so that's going to be negative q. So basically this negative 3 times q will be spread in between or distributed in between inner and outer surfaces. Inside the inner surface we will have negative q, such that within the dashed black line, which is the Gaussian surface, within the conducting material, the enclosed charge is 0, and the remaining charge, which is negative 2 times q, is going to be spread on the outer surface. Surface charge density is defined as total charge divided by the surface area. So on the inner surface of the shell, we have total charge equal to negative q, and the surface area of the inner surface is 4 pi a squared, since a is the inner radius of the shell. So then the surface charge density on the inner surface is equal to negative q divided by 4 pi a squared. In part C, we're calculating the surface charge density for the outer surface of the shell. On the outer surface, as we explained before, the remaining charge is equal to negative 2 times q, and the radius of the outer surface is b. So the surface charge density for the outer surface is going to be equal to negative 2 times q divided by 4 pi b squared. If we simplify this expression, we get negative q divided by 2 pi b squared. In part D, we're sketching the electric field lines, and we're also showing the locations of all the charges. Again, we have at the center we have positive q, that's a point charge. On the inner surface we have negative q deposited on the surface, and on the outer surface of the shell we have negative 2 times q. Now the electric field lines within the shell, inside the shell, in between the point charge and the inner surface of the shell, are pointing away from the point charge, which is positive, all radial electric field lines pointing away. Outside of the conducting shell, again the electric field lines are radial, but they're pointing inward towards the shell because that's negative enclosed charge. In part E of the problem, we're sketching a graph of E as a function of R, E being the electric field magnitude, which is positive. E is inversely proportional to the square of R, so that's what we call the inverse square law. So as R goes to 0, E goes to infinity. As R goes to infinity, E goes to 0, and it has a curved shape. And remember, in between A and B, in the region within the conducting material, E drops to 0. So for that part, we have a discontinuity, and we have a flat line at the 0 level.